We've been thinking all about how light interacts with the atom. And we've used the Bohr model of the atom to do this. In our last lesson, we figured out how to determine the energy of a light particle that interacts with the atom. In this lesson, we'll go all the way to wavelength, so we can think about the color of light that interacts with atoms. Let's learn. So here is our Bohr model of the atom. Remember, we have electrons in these rings around our nucleus. So say we have an electron there, and a photon comes by. Remember that a photon is a packet of light, and that photon is absorbed and kicks the electron up to a higher level in an absorption process. Our goal, whether that photon is absorbed or emitted, is to figure out its energy. That's what we did in the last video. Or to figure out its frequency, the frequency of light that corresponds to that photon, or its wavelength. And so in the last video, we found energy, and now we're going to learn how to go to frequency and to wavelength. Okay, let's take a look at the first equation we'll use. This equation we last saw in the photoelectric effect, and it relates E, that is the energy of the photon, which is always in joules, to the frequency of the light. That's that Greek letter nu that looks a little strange, but it's the Greek letter nu, and it tells us the frequency of light, which remember is how often we see a peak. The last thing we see in this equation is Planck's constant. This is what's called a constant of nature. And it's basically just something we go out in the world and we measure how much energy light has based on frequency, and that allows us to determine what Planck's constant is. And it's 6.626 times 10 to the minus 34 joule seconds. Man, that is a mouthful. But basically, for the purposes of solving our problems, what we need to know is we always have that value. It stays the same, and we went out and measured it in nature, and now we can use it always to go between the energy of a photon and the frequency of light. So let's do a few problems now where we start with how an electron moves between those rings and then eventually go all the way to the wavelength of light that we have. Okay, so first let's do frequency. This problem says a hydrogen atom absorbs a photon and an electron is excited. That just means moved up in energy levels from the n equals 2 to the n equals 3 level. It says, what is the frequency of the absorbed photon? So we're just looking for the frequency in this one. Remember, we're always going to write down a list of what we have. We know that our electron starts at n equals 2. And remember, we put the little subscript 1 there to tell us where our electron's starting. We know our electron ends at n equals 3. And we're looking for eventually frequency. This is the first time in this class where we've actually had to use two equations to solve a problem. And what you'll notice here is we've been given two n's, but we're looking for frequency. And when we look over at our equation in terms of n's, it doesn't have frequency, it gives us E. Okay, but then we have this other equation that relates E and frequency. What do we do here? Well, when we're solving this sort of problem, what we now want to add to our list of things that we need is our energy. Because we realize that if we get energy, we'll be able to solve for frequency because we have an equation for that. So the practical way to do this is just say, okay, I know I want frequency. Let's look through my equation list to find an equation with frequency. And what do you know? It's related to E, the energy of a photon. And so now if I can find energy, I'll be able to find frequency. So first, let's find energy. Okay, energy is equal to 2.179 times 10 to the minus 18 times 1 over my initial n, which is 2 squared, minus 1 over 3 squared. Now, in this case, what we're going to do is go ahead and plug that into our calculator to solve for the energy of our photon. When we do that, we're going to get 3.0 times 10 to the minus 19 joules. Very important that you're following along with all of these videos with your calculator. So that's just basically step one. We haven't gotten to our frequency, but we do now know our energy. So we know our energy, we know our N, we know our N1 and N2. And now we're ready to find our frequency. So to do that, we're going to grab our equation that has frequency in it. And that's right over here. Okay. So our frequency is going to be determined by this equation with Planck's constant and energy. So we'll start by writing down our equation, E equals h nu. Now notice in this case, we have energy and we have Planck's constant. We always have that, but we don't have this one. So we want to look for that one. That means we're going to need to do a little algebra. So what do? We want to get frequency by itself. Right now it's being multiplied by h. So to get frequency by itself, I'm going to divide both sides by h. That's going to make that h cancel out, and it will tell us that E divided by h is equal to our frequency. Make sure that looks like an h and not an n. And now we're ready to plug in our energy that we got from our last problem, 3.0 times 10 to the minus 19th. And we divide by Planck's constant, 6.626 times 10 to the minus 34. And remember, we just got Planck's constant from the top right here. We always have Planck's constant, and it's always exactly the same. It's always 6.626 times 10 to the minus 34. Here's a case where if you don't use parentheses on the bottom of that number, your calculator will do the wrong thing with that. So make sure as you divide to solve for frequency, you put that bottom number there in parentheses. When we do that, you'll get that the frequency is 4.6 times 10 to the 14th hertz. So the problem wanted to know, what frequency will the photon be that's absorbed when our electron goes from n equals 2 to n equals 3, and it's 4.6 times 10 to the 14 hertz. Remember that hertz is how often we see a peak in light. So if this light was traveling by us, we would see 10 to the 14th peaks every single second. So that's a really high frequency. Okay, the last thing we want to do is go from frequency to wavelength. And so this says a hydrogen atom absorbs a photon and an electron is excited from the n equals 2 to the n equals 3 level. That's the same exact problem we had last time. And so remember, we ended then with our frequency of 4.6 times 10 to the 14th hertz. So we're going to start there. But if we got this problem and we were starting from the very beginning, we would start by getting energy. That would be step 1. And then we would get frequency. That would be step 2 with that equation there. And then we'd get to step 3, the step we're going to do right now, which is solving for wavelength. Okay, so we know we have the frequency of the light, and we always have the speed of light, 3.00 times 10 to the 8th. And the units of our speed of light are meters per second. Light moves really, really fast. So frequency is equal to c over lambda. You want to hear a joke? This is the Greek letter nu. And so if you want to tell someone a joke who's a nerd, you can say, hey, what's new? And then they tell you something. And then you say, no, it's actually c over lambda. Yeah, it's kind of a lame joke, but to this day, I can remember that nu is c over lambda. So that's good news. All right, so we got nu equals c over lambda. And what we want to solve for is our lambda. Remember, we did this algebra in our intro to light video, but whenever we want to get lambda, and it's down in the bottom, we need to start by multiplying both sides by lambda. Just basically get rid of that fraction, and that really saves us a headache. So what that's going to do is cause the lambdas over there to cancel out, and we'll get lambda times nu equals c. Not as good of a joke in that one. And then to get lambda by itself, we have to divide both sides by nu. Remember, we're always doing the opposite of what our mathematical operator is in the equation. So here we're multiplying nu by lambda. So if I want to get rid of nu, I need to divide both sides by it. So I've gotten rid of nu now, and now I get my final equation, which tells me lambda equals c over nu. All right, and now to actually solve for that wavelength, I'm going to plug in c, which is 3.00 times 10 to the 8th, divided by our frequency, which we saw in the last problem was 4.6 times 10 to the 14th hertz. Again, this is a case where we're going to need to use parentheses in that bottom number to make sure we get the right thing. What should you get? Grab your calculator, check it out, pause the video. We should get 6.52 times 10 to the minus 7 meters. That turns out to be red light. So for this exact transition, if we had an electron drop from the n equals 3 to the n equals 2 level, we would shoot out a photon. And what color would it be? It would be red light. And so now we can understand how the specific changes that our electrons go through determines the color of light that comes out.
Hey, hey.